So my name's Josh Stuckner. I'm at NASA Glenn Research Center. So when Intelligence first gave us the Alchemite software and we got our hands on it, they said, oh, this is an excellent product. You can do all kinds of stuff, optimization, design, build machine learning models. But we really wanted to test it out for ourselves before we started incorporating it into our workflows. So this is the results of our evaluation. So we applied the data set, or we applied the technology to a couple data sets. The first is a data set of heat exchangers, which we had actually a machine learning hackathon on, so we had a lot of data and evaluation on that to compare to. And the second is some shape memory alloys, which we're developing at NASA, and so we evaluated how well the Alchemite engine works on that. So in the first data set with the heat exchanger, we were evaluating a bunch of different components, and they have a bunch of continuous features such as like the height and the width, the splay width, how much air flows over them in the component. And then there's also categorical features such as the base shape, whether circular or square, the configuration, which I think there's 7 or 8 different configurations of whether it's splayed out or how rectangular it was, stuff like that. And then it could be copper or aluminum. So we had both continuous and categorical features that we wanted to test. So in the first experiment, we were testing the thermal resistance, which we want to minimize. It's how much resistance there is to the heat exchanger putting heat away from whatever component you're trying to get heat away from. So that's what we're trying to target for prediction. So here are the results of our experiments with using the Alchemite engine versus using random forests with scikit-learn. And on the x-axis, we have the actual data. So we split the data set 80-20, as I show here, and 80% went to the random forest and Alchemite, and then 20% I kept for myself as like validation just to test how well the algorithms are performing. So these plots are of that held out test set, and we have the actual values versus what Alchemite predicted or the random forest predicted. And 100% accurate would be directly on this line. Of course, due to noise and measurements and the data itself, you can't always expect 100% accurate measurements. But by comparing it to the random forest, we can see that Alchemite has a better coefficient of determination. It's more accurate at predicting the results in this case. And we get uncertainty around our predictions, where here we're just given the value, but here we have a measure of how uncertain the model is in those predictions. Now, the other data set we tested it on was shape memory alloys. So if you don't know, shape memory alloys kind of, they can remember what shape they are at a certain temperature. And then you may have seen the videos of like paper clips, you can like deform, and then when you like set a flame to them, they'll remember that shape and go back to them. So NASA's exploring them as new tires for rover wheels, and also for to change the configuration of wings in flight. So we have pretty equal predictions with the Alchemite engine from the random forest, but you also have to remember that we built separate random forests for every single target we wanted to hit. So we're hitting 6 different targets and only one Alchemite engine to give us that global view so that we could do optimization over the whole global like high dimensional space. Also, the Alchemite engine gives you uncertainty quantification. So now what I wanted to test was how well will it perform if we just start adding holes to our data. So what we did was randomly removed 20% of the data cells. So maybe a measurement here, a measurement there. We just like randomly removed them and to see how well it would do the prediction. And then again, kept the 80-20 split. Now we couldn't compare this to the random forest models because we didn't have an easy way to fill that missing data. So we just are looking at the Alchemite here. And the predictions without hole or with holes, yes, it's reduced, and that's what you expect. You're giving the machine learning model 20% less data, but with a random forest, you can't do this at all. So even if you don't take every measurement, you can still make predictions and get insight on your data. So, in conclusion, yeah, the Alchemite engine, our evaluation showed that it is giving accurate predictions and what we expect. It's fairly easy to use. You don't have to build your own machine learning models by yourself. Now, I was using the backend engine, and so the web interface is even easier to use. And I've played around with it a little bit, and Tom will show more about that. Um, and it has a lot of great features that it can handle missing data, so we don't have to throw away rows where we didn't take every measurement. The uncertainty quantification is extremely invaluable and also necessary to do the inverse design of materials. It can determine which features are important, so you could maybe not do every measurement if you determine that like oh, the microstructure features aren't really actually that predictive. Often they are, but maybe not in this case. They're not. So you don't have to spend all that money doing microscopy analysis for this case. It can do optimization, use it as a design tool, and it can also. This is something that we were hoping to test out soon, and to start employing in our workflows is the ability to suggest the next experiment.